So I hope that my screen is visible to all of you.
Yes, sir, it is visible.
Okay, so let me start the session. So in this particular talk, I'm going to discuss one important aspect of this blockchain technology. So I guess that by this time, all the participants have a kind of broad overview about what is blockchain and how it typically works. So what I'm going to do that I'm going to talk about one important aspect of blockchains that is kind of prevalent in today's research space as well as for the industrial development, and it has become a real problem behind the practical deployment of blockchain-based solutions. So the idea is called interoperability. So we'll see that what interoperability means in the context of blockchain and how we can support interoperability on our top of a blockchain-based architecture or a blockchain-based application. So as you might already have heard of that, there are myriad of applications that can be developed on top of blockchain, including supply chain management, verification of the personal identification like the KYC verification, apart from the classical cryptographic and the banking sector applications, which are there on top of blockchain. And all these different applications, they have been developed by utilizing different types of blockchain platforms. So if you just do a simple Google search to find out that what is the available blockchain technology to develop certain kind of applications, you will see that there are multiple different type of platforms which are available today, including Ethereum, Corda, Hyperledger. Within even Hyperledger, you can see different types of flavors like Hyperledger Fabric, Hyperledger Barrow, Hyperledger Sawtooth, Indie. So all these different kind of platforms are available. So one natural question comes that which platform I am going to choose to develop a particular application. And indeed, what happens that this particular choice is not very straightforward. Rather, it depends on the type of applications that you are going to develop. And at the same time, the amount of investment that you are going to do while developing the application, because all these different kind of platforms which are available in the market, they have their pros and cons. Now, depending on these different enterprises, they choose different platforms to develop their applications. And as a consequence, we have seen that in the enterprises, different kind of applications have been emerged over time by utilizing different platforms. So if you simply ask me that I want to build up this particular applications or this particular decentralized app or dApp, what particular platform do I choose, that whether I'm going for, I need to go for Ethereum or I need to go for Corda or I need to go for Fabric. There is no straightforward answer to this question. And it remains a kind of personal choice to choose one of those platforms to develop subsequent applications. And as a consequence, what has happened in today's global marketplace, that different applications, they are utilizing different blockchain platforms. So some are using their available blockchain platforms, some are using the commercial platforms, and some are building the platform from the scratch. Well, so as a consequence, we landed up on this particular problem of blockchain interoperability, and that is the kind of hot topic which are in discussion in today's research space as well as in the industry perspective, that how we can support interoperability on top of blockchain architecture. So this particular talk will discuss about the different kind of interoperability platforms that we have blockchain by exploring such kind of interoperability platform. And finally, we touch upon that what are the kind of open research areas in this aspect that you can take up or someone can explore further to expand the horizon. So let us start with this particular discussion. And just before I enter to the technical topic, just a kind of information for all of you that whenever you feel that you need certain kind of clarification or you have certain kind of questions, please feel free to stop me and ask the question. So let us make this talk interactive. Like feel free to share your views about the different parts of the talk that I'm touching upon, and let us proceed in that way. Well, so there is no hard and fast rule that you have to ask the question at the end, or you need to wait till I stop and give a break for a question. So let us proceed. So as I was mentioning that if we look into the current horizon of the blockchain platform, then we typically have two different type of blockchain architecture. One is the public or the open blockchain architecture that we call as the kind of permissionless architecture. Another architecture is a kind of private or a closed blockchain network that we call as the permission. Now, typically in a public or an open network, anyone can participate in the blockchain platform. So the classical cryptographic cryptocurrency-based applications like blockchain or even smart contract applications like Ethereum, they use a kind of permissionless model where there is no restriction about who can join in the blockchain and what they can do on top of blockchain. Rather, anyone can join the network and start initiating the transactions. Whereas the enterprise network, they basically governed by this private or the closed model of blockchain, which we call as the kind of permission model of blockchain. So they typically use such kind of permission model of blockchain. And in that permission model of blockchain, what happens that we have a set of pre-authenticated and pre-authorized participants who participate in the blockchain-based architecture or the blockchain-based services. Now, although the participants are pre-authenticated and pre-authorized, but they can still behave maliciously. And because of that reason, this idea of blockchain is basically applied on top of a kind of closed network. So it is something like that. In a closed network, you know that who are going to be your neighbors or who are going to participate in the network, but you still do not trust those participants. So, for example, in a supply chain network, so in a typical supply chain network, we have different kind of participants like the vendors, the distributor, the wholesalers, the last mile shopkeepers, and all these participants, they are competitor to each other, and as a result, any one of them can behave maliciously, and that's why we do not trust them as such. Well, so that's why we still want to have a kind of blockchain-based, decentralized smart contract platform on top of those architecture. So that way, over the times, these two different types of blockchain platforms have been emerged, and different applications, they have started using different kind of blockchain platform, as I was mentioning earlier. That some applications, they have used public or the open blockchain platform. They have developed applications on top of smart contract architecture like Ethereum, whereas there are applications which utilize this kind of private or the closed environment to provide transparency in the process, like the supply chain management, identity verification, those kind of applications. So if you just look the type of different platforms which are available to facilitate these two different type of blockchain platforms, the public platform and the private platform. So you will see that there are different type of various solutions which are available. So in the public domain, starting from Bitcoin, we have Ethereum, Ripple, Litecoin, then Omnisgo, Zcash, Nexus, Dash. So all these different kind of platforms that have been emerged. Similarly, in the private or the closed domain, these platforms like Hyperledger, Corda, Multichain, Quorum, all these different kind of platforms have been emerged over time. Now, if you just look into the spectra of applications that have been there in the market or that have been developed on such kind of architecture, you will see that, well, different types of applications have been actually evolved over time. So it is something like that. Certain application they prefer Ethereum. Many other applications they were built on top of Dash or Nexus architecture. Similarly, in the private or the permission domain, people have used Hyperledger for developing their applications, Corda for developing their applications. So different applications have utilized different kind of blockchain platform. Well, and as a consequence, what has actually happened that the entire solution space it has emerged or it has basically expanded to a kind of multi-platform architecture. So it basically means that different solutions are utilizing different kind of platforms. Now, I just want to point out to these particular things called National Strategy on Blockchain. I think many of you already know that in January 2021, Government of India under Ministry of Electronics and Information Technology, they have published this National Strategy of Blockchain, and in that particular article, they have explained the kind of architecture that they are going to support on top of blockchain. So they basically propose to develop a kind of national blockchain infrastructure where you can design, deploy, and run your own applications which are built on top of blockchain. And this is the kind of architecture that have been proposed to build up this national blockchain infrastructure. So if you look into this architecture, at the bottom layer, we have the different kind of regional nodes which are...
wants to ask some question.
Can you please repeat?
One participant is asking something.
Yeah, sure. Please go ahead.
Sir, to add on with this national strategy on blockchain, Niti Aayog of India has turned on the project that is India Chain, which is having the Internet of Value as a second slot from 2020 onwards, which has been added what the national strategy which you are explaining right now with the India Chain project itself.
Right. So I couldn't catch up your question. Can you please repeat once?
No, sir. I'm just adding some information about this Chain India project. India Chain project is a...
Right. Yeah. So actually, from the government side, there are multiple different projects which are there and which are
developing by the Niti Aayog of India as this national strategy on blockchain. What you are delivering now?
No, this is not the one that had been published by Niti Aayog. So Niti Aayog, they had in 2020 around that time they had published one draft concept note for utilizing different kind of blockchain-based solutions, and as a part of that, they have actually taken up multiple pilot projects. So, like they had a pilot project on, say, automating the kind of digital certificate provisioning from different universities on top of blockchain-based solutions. So that way they have taken up 4 different pilot projects. But this particular article is different from that. So this is something that got published in January 2021 from MIT that actually published a draft national strategy on blockchain, and they asked for the public view on top of that. And in that draft national strategy on blockchain, they were talking about, or that was actually came based on the success of the pilot projects which had been taken by the Niti Aayog. And this particular document, this is publicly available. You can just do a Google search and download this document and can check it, the different kind of aspects that MIT has tried to focus on. And in this document, they have particularly talked about the kind of infrastructure that India requires to support blockchain-based applications and to develop blockchain-based support systems, and the kind of applications where government is trying to give focus
on. Okay, sir. Thank you.
Okay. Yeah, so as I was talking about that, one of the primary focus of this particular article was to propose a kind of infrastructure support for providing blockchain-based solution or to develop, implement and test blockchain-based solutions on top of a platform. And this kind of platform support, what they call about the national blockchain infrastructure. And if you look into this architecture, this particular architecture actually talks about having different regional nodes at the bottom, which will provide a work like a kind of support. They will provide the hardware infrastructure, and on top of that, you can have this chain layer that can actually have different blockchains corresponds to different applications. So you can have a blockchain for property management, you can have a blockchain for healthcare management, a blockchain for smart city management, a chain for educational management, and so on. And this is not only about a single chain, but in each of these vertical, there can be multiple such blockchains. And the part where we are actually mostly interested on top of that, which they are calling as the platform layer, and you see that this platform layer actually supporting different kind of blockchain platforms. So it is providing support for Fabric, it is providing support for Sawtooth and support for Corda and so on. Well, now the interesting fact here is that whenever it is providing this platform layer and providing support for different platform, it is ideally that whenever you are building up an applications on top of such kind of infrastructure, different applications will be built up on different kind of platform. Well, so that is the kind of pivotal point and the key point where we would like to focus on in today's discussion. That it is not like that every solution is going to get converged to a specific platform, but rather different solutions might pick up different kind of platform. And that actually raises the requirement of having a kind of interoperability between multiple different platforms, because I will show you certain examples where you will see that it is highly possible that you actually want to initiate a transaction between two different solutions. Well, and these two solutions are built up on different platforms or sometimes on different chains, even they are using different platforms. So for example, it might happen that you have an healthcare solutions, you have a solution for insurance management. Now this insurance management network was built up on one blockchain and the healthcare solutions have been built up on another blockchain. So the hospital network is built up on another chain. Now, if that is the case, then there is a requirement that, well, whenever you are going to an hospital, you need to get connected to your insurance company, and for that reason, the blockchain which is supporting the hospital network, that blockchain need to talk to the blockchain which is supporting the insurance network. Well, so you basically need a kind of information transfer from one blockchain to another blockchain. And here comes the kind of bottleneck, because this kind of security, privacy, immutability, all these different kind of guarantees that we heard of while developing a kind of blockchain-based solution, all those kind of things are basically confined within a single blockchain network. So whenever you are going off chain or you are going out of the chain, those kind of security guarantees are not being provided. Well, now the question comes that whenever I'm going to transfer information from one blockchain to another blockchain, who is going to validate that information? Who is going to provide the security of that information? Now the classical approach was that, well, you use some third party exchange. So typically that was developed in the context of money transfer between two different blockchains. So for example, transfer of Bitcoin from a Bitcoin network to Ethereum network, just like we make a transaction between Indian currency and dollars or other foreign currencies. In a similar way, if you want to buy Ethereum with respect to some Bitcoin, then how you are going to transfer the Bitcoins from the Bitcoin network to the Ethereum network. So traditionally, different exchanges have been formed, but these exchanges are something like, again, a centralized entity, which violates the basic principle behind utilizing blockchain. So what blockchain says that I don't want to go to a centralized solution, rather I want to stick to a complete decentralized solution. So this basically brings up a kind of open research challenge, that how will you develop solution to support interoperability between two different blockchain networks? Now, depending on the context, You might need interoperability from a public network to a private network, or you might need interoperability between two public networks, or you might need interoperability between two private networks. So in this particular talk, we are actually going to look upon all these three different concepts. So we will start with this permissionless blockchain interoperability that basically says that how you are going to transfer money or transfer assets between two different open blockchain network or two different permissionless blockchain network. So, as I was mentioning at the beginning that these blockchain networks have been starting as isolated silos. So that means every individual network works on their own. If you have a Bitcoin network, the Bitcoin network works their own, and if you have an Ethereum network, the Ethereum network works their own. So in that context, how we can support this kind of cross-chain transfer, that becomes a kind of open problem. So typically these blockchain-based cryptocurrencies, they enable secure and trustless currency transaction between the parties. Well, now, if you just look into the spectrum of different cryptocurrency applications which are there in the market, there are nearly 2,000 different cryptocurrencies which are currently in operations. Well, and separate blockchain networks with often different protocols and standards are used for these different cryptocurrencies. So if you look into the Bitcoin network, and if you look into the Ethereum network, or if you look into the kind of Litecoin network, these networks, they basically have different set of protocols or different way to validate the transactions. Well, and as I was mentioning that these networks continue to operate in complete isolation from one another. And as such, there is no kind of connectivity between the two networks. Well, so here comes the problem of interoperability, that if you want to make a transaction from a Bitcoin network to a Ethereum network or vice versa, how you are going to support it. Well, so from there, this particular problem of cross-chain asset transfer that comes, say for example, in Bitcoin network, I have an account and I also have an account in an Ethereum network, and I want to transfer one Bitcoin from the Bitcoin network to the Ethereum network. How I am going to do that? So you can just relate this problem to the typical money transactions problem or the cross-currency money transaction problem, where you want to transfer $1 from US to your US account to your India account, from your US account to your India account. Now, if you want to do that, typically these banks that facilitate this kind of transfer, that means whenever you are initiating a transfer of $1 from your US account to your Indian account, the corresponding bank, they actually check that what is the currency conversion rate on that particular day, and accordingly they make that particular transactions. That if you are transferring $1 from your US account, then you will get around 75 or 78 rupees in your Indian account, depending on the transaction rate of the day. But how can we do such kind of transactions on top of a blockchain-based architecture? Because see, in our normal market, the banks are the authorities who are going to do that. But this blockchain network or the kind of cryptocurrency network, they are actually, we try to get rid of such kind of banking system. So we thought of that, well, we will have a monetary system where there would be no central party or no one who are going to control us. Well, so that way the banking system is not there anymore. And if the banking system is not there, then who is going to do such kind of transactions? That if you want to transfer one Bitcoin from your Bitcoin network, then you will get the equivalent number of Ethereum, that is, say, for example, 33 Ethereum in your Ethereum network. So this kind of transfer is not only between my account in the Bitcoin network and my account in the Ethereum network, that can happen between different accounts as well. So for example, Alice wants to transfer money to Bob, and Alice is belonging to one network, that is the Bitcoin network, and Bob is belonging to the Ethereum network. Now, if Alice wants to transfer the money, Alice will transfer Bitcoin from her network, and that will be credited to the Bob's account in the Ethereum network. So that kind of cross-chain asset transfer requirements are there. Well, now to do this kind of transfer, what Alice have to do, that Alice must use some kind of third party who owns more than 33 Ethereum. And that third party has account in both the network and that third party operates on both the network. So what can happen that you can have a kind of trusted third party. That trusted third party has accounts in the Bitcoin network as well as in the Ethereum network. So Alice makes a transfer of one Bitcoin to that person, and that person then transfer 33 Ethereum network from his or her wallet in the Ethereum network. Well, so that way you can utilize a trusted third party to facilitate such kind of cross-chain asset transfer. But the problem of such kind of using such kind of TTP or trusted third party is that that can be a kind of possible security violations, or there can be multiple different security issues which can come. Now, interestingly, because of to support such kind of cross-chain asset transfer, there have been hundreds of such centralized cryptocurrency exchanges which are available in the market. So if you just do a simple Google search, you will see that there are many cryptocurrency exchanges where you can sell Bitcoin and from there you can buy Ethereum, or you can make a transaction from one cryptocurrency to another cryptocurrency. Well, but the problem with such kind of TTPs are that they are centralized. Well, so basically you are transferring your ownership of your funds to the sole control of the exchange administrator. So you are transferring that one Bitcoin to that particular third party or the exchange with an expectation that the exchange is going to transfer 33 Ethereum to the Ethereum network, right? So that way you are actually explicitly trusting the exchange that the exchange will not do any kind of malicious activity, but rather the exchange will do the kind of correct transfer by taking one Bitcoin from you and transferring 33 Ethereum to your friend. Well, so the advantage of using such kind of exchange or trusted third party is that the transaction is very fast. So once you are depositing the money to the exchange, then the exchange can immediately transfer the amount to the other network. But the problem is the lack of security. Right? As I have mentioned that you are explicitly putting your trust on the exchange that they are not going to do any kind of malicious behavior, but that didn't happen in the reality. So if you look into the history, there have been numerous cases of theft from such kind of centralized exchanges. So for example, this MTGOX exchange that suddenly shut down in 2014, and that way around 650,000 Bitcoins were lost, well, which were in possess of this MTGOX exchange. Similarly, this Bitfinex exchange, they lost approximately 120,000 Bitcoins in 2016. So that way, if you look into the history, there are numerous cases of such kind of exchange failures. Because of such exchange failures, there are instances where people have lost their Bitcoins because they have made the transfer to the exchange, but in return they have not received the corresponding money in the other account. So that way, although this kind of exchanges provide a kind of solution for transferring money from one network to another network, they have significant amount of security concerns. So from that particular question, we try to look into this problem of asset exchange. So what this asset exchange or how this asset exchange can work, that assume that you have a Bitcoin network and an Ethereum network, and Bob is this kind of exchange or the trusted third party who is having account in both the Ethereum network as well as in the Bitcoin network. Now, when Alice transfer one Bitcoin to Bob, then Bob transfer 33 Ethereum to Alice. Okay. Now, the interesting thing is that to ensure security in this kind of cross-chain asset transfer architecture, what we need to ensure that these two transactions, transaction one, where Alice is transferring one Bitcoin to Bob, and the transaction two, that where in Ethereum network, Bob is transferring 33 Ether to Alice, these two transactions need to be atomic. And what we mean by an atomic transactions? An atomic transactions means either both the transactions will succeed or both will fail. So it is not like that only transaction one will succeed and transaction two will fail. If that is the case, then you will see that the system is there in an inconsistent state, and we do not want that. Well, we want that both the transactions should get executed, and that's why we want to support such kind of atomicity property on top of this architecture. But the problem of such kind of asset exchange that without the presence of any escrow, the funds are in the control of the sender and the receiver parties. Well, it might happen that one party might abort the exchange after receiving fund. So Bob just received the one Bitcoin from Alice, and immediately Bob aborts from the protocol. If that is the case, then Alice has actually lost her Bitcoin and she has not received the corresponding Ethereum from Bob. Well, and there can be problem of synchronization between the two networks as well as the sender and receiver, because as you already know that we are working on a complete distributed network, and ensuring synchronization distributed network is never possible. So that way, such kind of synchronization problems are already there. It might happen that Bob's account in Ethereum network and Bob's account in Bitcoin networks are not perfectly synchronized, and if that is the case, then it is difficult to track that whether the transaction has been executed successfully or not. And the final problem is the difficulty in agreement on exchange rates, which may keep on changing every second. So if you have seen that this exchange rate between two different currencies, for example, from US dollar to Indian currency, that keeps on changing, right? And it might keep on changing at every second. Now, if that is the case, then who is going to track, or who is going to keep a note of such kind of current exchange rate? So that too in a kind of complete distributed or a complete decentralized architecture. If it had been a centralized architecture, this problem was much more easier, because in a centralized architecture, the central authority or the exchange can keep track of the current exchange rate, and that typically happens in today's monetary transfer. That whenever you are going to buy some dollars in exchange of your Indian currency, the exchange will actually look into that what is the current exchange rate, and it will provide you the equivalent currency in Indian rupees. But supporting this is problematic in a complete decentralized network. So here comes the question that how we are going to support atomic exchange on top of such kind of decentralized architecture or decentralized network. Well, so from that particular aspect, this protocol got emerged, which basically says about this cross-chain asset transfer using atomic exchange. So the idea is that you have an exchanger. So Alice wants to transfer money to Bob. Alice is there in the Bitcoin network and Bob is there in the Ethereum network. So what Alice does, that Alice transfer one Bitcoin to Jack, who is the exchanger. In return, Jack transferred 33 Ethereum to Alice, and then Alice transferred that 33 Ethereum to Bob. Okay. Now here, what I need to ensure that transactions 1 and 2 must support the atomic exchange principle. That means the moment Alice is transferring this one Bitcoin to the exchanger, that is Jack, immediately Jack is going to transfer 33 Ether to Alice. And in that way, either both transactions 1 and transaction 2 will succeed, or both will fail. Now, once Alice is received that 33 Ether from Jack, then Alice can transfer that amount to Bob, which is the transferring of the amount that can run asynchronously from the atomic exchange protocol. Well, so that way, if you can solve this atomic exchange protocol, that means support that, well, I could have a protocol between the sender and the exchanger that either the both way transaction will succeed or both will fail, then that will solve my problem of asset transfer from Bitcoin network to the Ethereum network. So we are going to discuss about this particular solution called atomic cross-chain swap that got published in POTC 18, and this got very popular in the Bitcoin and Ethereum community for doing the cross-chain asset transfer between two different networks. So this atomic cross-chain swap protocol defines atomicity as follows: that an atomic transaction is an indivisible series of operations such that either all occur or none occurs. Well, so the idea that I have just explained to you. Now, an atomic exchange protocol or an atomic swap protocol guarantees that if all parties conform to the protocol, then all swap takes place. If some parties deviate from the protocol, then no conforming party ends up worse off, and no coalition has an incentive to deviate from the protocol. So that basically means that if everyone conform to the protocol, then the swap takes place. That means I am transferring one Bitcoin to the exchanger, and the exchanger is going to return back 33 Ether to me. And if some parties deviate from the protocol, then the remaining parties remain in the same state. So it doesn't happen that if some party deviate from the protocol, then it affects the balance of the system. Well, and typically, if you form a coalition within the network, then no such coalition exists which has an incentive to deviate from the protocol. So if they want to deviate from the protocol, they will not get any kind of additional incentive. So that this kind of atomic swap protocol guarantees. So the basic idea of this atomic swap protocol is something like that. So what I want to do that I want to transfer one BTC from Alice to Bob, and Bob is going to return 33 Ether from his account in the Ethereum network to Alice's account in the Ethereum network. And these two transactions should execute simultaneously. Well, and we need to ensure that either both the transaction happens or none of the transaction happens. So what we do that we first initialize smart contracts on both ends of the account. Well, so what Alice does, Alice set up a contract in the Bitcoin network, and that particular contract transfers one BTC from Alice to the contract. And yeah, so this is the first step. So in the first step, Alice transfers one Bitcoin to this contract. So first this contract A and contract B are submitted in the corresponding network. Well, so Alice submits this contract A to the Bitcoin network, and Bob submits this contract B to the Bitcoin network. And after that, Alice makes a transfer of one BTC to contract A, and Bob transfers 33 Ether to contract B. You see that this corresponding amount, that means the Bitcoin and the Ether, they are not in the possession of Alice and Bob. Rather, contract A contains one BTC, and contract B contains corresponding 33 Ether. Well, now the thing is that once these contracts get executed, then the system will be able to transfer the corresponding amount. Well, so what we need to ensure that, well, once the contracts have the corresponding amount with them, then we want to trigger certain common event, and that particular event will do the reverse transfer. That means contract A will transfer one BTC to Bob, and contract B will transfer 33 Ether to Alice. Well, and you see this actually guarantees that finally, once these two contracts are getting executed, then one Bitcoin has been transferred from Alice to Bob, and 33 Ether has been transferred from Bob to Alice. Okay, so this is the kind of guarantee which we are providing while executing the corresponding contracts. Well, and the interesting fact here is that although Alice and Bob, they can do malicious activity, but by the time they are submitting the contract to the corresponding network, by the virtue of the smart contract execution, this contract will anyway get executed. Well, and once the contract gets executed, you will get the corresponding money back. But the important question comes that how you are going to design this common event that is going to trigger the contract. Okay, so if you can design a common event which is going to trigger the contract, then your problem gets solved. So that is the particular challenge which we have right now, and this particular challenge we are going to solve with the help of certain concept called hash lock. Okay, so what is a hash lock? So hash lock is a type of encumbrance that restricts the spending of an amount until a specified secret key is publicly revealed. Well, and the inherent property of the hash lock is that once any hash lock is opened publicly, any other hash lock secured using the same key can also be opened. So here is an example. So let us look into the example. So the example says that say Alice generates generates a secret key, I love strawberries. Okay. Now once Alice generates this secret key, what Alice does, so Alice computes the cryptographic hash of this key, which is this large number. Well, now what Alice does, that Alice initiates a hash lock contract of 1 BTC, which has the condition that if the key is revealed, then pay Bob with 1 BTC. Well, and this particular contract also contains the hash, which allows any miner to verify the corresponding key. So that basically means that this particular hash that you are generating, these hash have been incorporated in the contract. Well, and the contract is submitted to the network with this corresponding hash. Now, once you are revealing this key, that the key to this hash is I love strawberries, at that instance, the contract get opened, well, because the hash get revealed. Once the contract get revealed, then both the contract which are containing this hash, they get executed. Okay. Now let us see that how we are going to use this kind of hash lock to execute the protocol. So what we are going to do, apart from hash lock, we use another lock called time lock. So time lock is a type of smart contract primitive that restricts the spending or transfer of some currency until a specified future time. Well, so for example, you can use block height as a proxy for time. So what you can say that, well, so if the contract doesn't get executed within the next 30 seconds, then this contract will get void. Well, so you can put up a constraint on the contract that the contract need to be executed within that amount of time. Well, so let us see that how we can utilize this hash lock and the concept of time lock to support the atomic exchange protocol. Okay, so what actually happens in case of a hash time lock contract or HTLC? In case of a hash time lock contract or HTLC, Alice submits 1 BTC. Okay, so once Alice submitting 1 BTC, it creates a funding contract, and in that funding contract, it provides a hash lock. So Alice knows the key. Say the key is that I love strawberries. Say, yeah. Say the key is I love strawberries. Well, and once you have the key, then say K is the key, and this is the corresponding hash that has been put in the contract, and along with that, I put a timing constant that is 2 delta. Well, now once this key is being revealed, well, once Alice make this key public, that means I love strawberries have been public, and at that time, this contract get executed and the money gets transferred to Bob. Well, otherwise, if Alice doesn't reveal the key within this timeout duration 2 delta, that means if time greater than 2 delta, then this contract gets void and the money gets returned back to Alice. Well, so with this particular HTLC architecture, let us try to see that how the atomic swap protocol in HTLC works. So let me not go to the text, rather try to explain you with the help of a timing diagram. So what happens that Alice generates the secret key and compute the hash. So after Alice has generated the secret key and computed the hash, Alice submit the HTLC or hash time lock contract to Bitcoin network with 1 Bitcoin, the corresponding hash value H, and the time lock value 2 delta. Now, once this contract is available in the Bitcoin network, Alice transfer this hash to Bob. Now, once Bob gets this hash value, what Bob does, Bob verifies that Alice has already created the funding contract in the Bitcoin network. Well, so that can be verified by checking whether the hash is there in the contract or not. Well, so once that verification is being done, Then Bob submit a contract to the Ethereum network with the same hash with 2 delta and corresponding transfer of 33 Ethereum. Well, so these two particular contract, one to transfer for the Bitcoin and another to transfer from the Ethereum, they get submitted in the corresponding network. Now, once you have these two contracts submitted and both the parties have verified the contract, then in the similar way, Alice can also verify that Bob has created the funding contract with H in the Ethereum network. Now, at that point of time, if Alice is sure that the contract has been created after verification of the contract, Alice can reveal that. Okay, so what Alice can do, Alice can redeem this contract at the Ethereum network with the key that I love strawberries. Well, at the moment Alice is actually making her hold on this particular contract that has been submitted on the Ethereum network by Bob, Alice needs to reveal the key, and that way the key has been revealed and Bob can know the key. And once Bob knows the key, then Bob can also redeem the corresponding contract with that key that I love strawberries from the Bitcoin network, and the money is paid to Bob. So that way, this contract gets executed, and it ensures that, well, the moment both the parties have verified that the corresponding contract has been submitted in the network and they reveal the key, at that particular moment, the contract gets executed and the corresponding parties will get back their money. Well, so that way you see that with the help of this hash time lock contract, 1 Bitcoin has been transferred from Alice to Bob, and the equivalent 33 Ethereum has been transferred from Bob to Alice. Well, now what happens when Alice refuses to reveal the key? Now, if that is the case, that means if Alice reveals reveal the key, then we have the time lock, which is also there in the contract. So the timeout will happen. The moment timeout will happen, that 1 BTC that was submitted by Alice in the Bitcoin network, that the money will return back to the Alice. Well, similarly, this Ethereum, that will also see a kind of timeout after this 2 delta time, and 33 Ether will be refunded to Bob. So that way you see that whenever the contract is getting executed, during that time, both the parties are able to get back their money. Either both the parties are able to get back their money, or if a timeout occurs, then both the contracts get void and none of the transactions actually happens. Well, so that way with the help of this hash time lock contract, you can do a atomic swap on top of 2 different cryptocurrency network, and this concept of HTLC became very popular not only in the academic community but also in the industry, and different exchanges have now started using this kind of hash time lock contract based architecture so that they can ensure the transfer of the money in a trusted but guaranteed way. Well, now in hash time lock contract, there can be kind of complex variation of this protocol. Say, for example, yes, any question?
Sure. As you told in the previous slide, that the entire transaction where Alice got the sent the coin, 1 Bitcoin to Bob, the entire scenario what you showed in that slide, where the entire this cycle shows, right? So, is there any set of tampering that could occur in this line while sharing the hash function or verifying the code which is being created for fund sharing? Is there any chances of tampering from blockchain, Bitcoin to Ethereum network? 2 different networks, right? 2 different cryptocurrencies. So, is there any tampering that could happen in real time?
But how you are going to tamper it? Well, because see, the thing is that here, what you are going to submit, you are doing everything through the help of this smart contract, which is getting executed in the corresponding network, right? Now, whenever you are submitting the things, submitting something on a blockchain, say for example in the Bitcoin blockchain, by the virtue of the blockchain property, it is anyway tampered. Well, so that means, well, if you say that, well, I have generated certain key from the hash, I have generated certain hash. Okay. So as I was mentioning that this kind of hash time lock contract or HTLC can also be used to transfer money between multiple parties. So you can use HTLC to transfer money from A to B, then B to C, and then C to E, C to A. Well, so that kind of cycle can also be formed. Just for the interest of time, I'm not going to the details of it, but you can look into the policy paper to get the details about how such kind of cycles can be formed and complex transactions can be executed with the help of HTLC. Okay, so one particular limitation of this approach, this HTLC, is that it is very slow. Well, so it is slow in the sense that it often takes hours to execute. Well, because you are submitting the contract and then you are going to reveal the key, and the moment you are going to reveal the key, then only the contract will get executed. So it entirely depends on when the parties who are going to prepare that contract, when they are going to reveal that. And that way, the entire process is very slow. And because of that reason, the parties cannot respond to real-time price fluctuations. Okay, because it might happen that you agreed on some kind of transfer rate, and by the time you are creating the corresponding HTLC and revealing the key, the amount got changed. So you cannot make any change in the contract at that point of time. Well, and this kind of attack is sometimes vulnerable to a weak denial of service attack, where an adversarial party repeatedly proposes an attractive swap and then fails to complete the protocol, triggering refunds but temporarily rendering assets inaccessible. So what basically does that you create multiple such different contracts, but do not execute those contracts. So that way you can actually make the network busy by processing the transactions that you are submitting with the help of those contracts. So this is the kind of a very popular protocol, protocol for atomic cross-chain swap or to transfer assets from one cryptocurrency network to another cryptocurrency network with the help of this hash lock and the time lock. And as I was mentioning, that this protocol have been widely used right now to support transferring of money from one cryptocurrency network to another cryptocurrency. So any questions or any query up to this point that I have explained till now? Okay. So then let me move to the next protocol. This I will go a bit quick just to give you a kind of overall idea about how this protocol actually works in practice. So this protocol is called as Tesseract that got published in CCS 2019. So in contrast to HTLC or hash time lock contract, this particular protocol is real time. So it is as fast as centralized exchanges. Well, so the idea of this protocol is that, well, you can bid and sell. That means you can mention that I am going to sell Bitcoin at this particular price, and that price can be changed in real time, and someone can buy the Bitcoin and pay you the equivalent Ether in the price in which you are bidding. Well, so it supports cross-chain asset exchange, and it is secured against theft by the exchange operator. So what actually happens to Tesseract takes help of one hardware component that is called a trusted execution environment, or T. Well, so T is basically a kind of hardware component that provide secure execution of certain instructions. So for few of you who do not know about PE, I think that you have heard about that Intel SGX or Intel secure computing platform. So what does secure computing platform or the trusted execution environment or trusted computing platform provide? So they provide a hardware component within your CPU that actually does the computation in a secure way. So that basically means that you are providing the security by means of hardware interconnection. So the hardware is actually going to provide you the security. So within your operating systems, you can have a trusted execution of the operating system that will provide you prevention against different kind of attacks. So that basically means that whatever instructions you are going to execute on top of a TE, that set of instructions is difficult to alter. So as an attacker will not be able to access those instructions, and the attacker will not be able to make any change in those instructions which are getting executed on top of a trusted execution environment or TE. Well, so nowadays, different hardware component, they comes with their own trusted computing platform. One example that I have given you is Intel SGX. So apart from that, our tiny Raspberry Pi boards nowadays, they also have their own TE component. So you can configure it and you can execute the codes in a trusted way within those hardware platform. Now, in context of Tesseract, TE enables Tesseract to behave like a trusted third party. So that means this kind of cryptographic exchange, the instructions corresponding to that, you execute it on top of a TE environment. So, and the TE environment is actually supporting this kind of atomic execution of the transaction. So the TE actually ensuring that either all the subcomponents of the transactions will get executed or none will get executed. So this is the kind of architecture. So this is a kind of standard architecture for a trusted execution environment. So this trusted execution environment is basically a secure area within the main processor. So within the hardware, you can see that a set of protected hardware resources are there, which is the part of the TE. And you can run a typical embedded operating system where you can run different kind of untrusted app. And at the same time, you can have a secure world where you can run a trusted OS. That trusted OS is actually access these protected hardware resources with the help of the TE. And on top of that trusted OS, you can run the trusted apps. Okay. So this Tesseract app actually works like a trusted app on top of this trusted OS. So TE basically guarantees the code and data loaded inside to be protected with respect to isolated execution, integrity of applications, and confidentiality of their asset. So that means they provide these services, isolated integrity and confidentiality. So that thing that is getting executed within the trusted OS, any other third-party applications or the real-world applications cannot access those executions which are getting done on top of the trusted OS, and they will not be able to alter those. Okay. So this trusted execution environment actually provides an attestation that an output represents the result of an execution in the key. So what happens that in case of Tesseract, we have this real-time exchange which is implemented on top of TE. Now from Bitcoin network, you initiate a transaction. So while initiating a transaction, you can submit such kind of bits that you have one Bitcoin, you can want to sell that Bitcoin at a price of 305. And on the other hand, when that Bob wants to purchase some Litecoins, so the Bob can say that, well, I want to purchase 500 Litecoin at a price of 299. Okay, 299 Litecoin per one Bitcoin. So that way, these bids and sales are submitted to the TE real-time exchange, and the TE real-time exchange can actually find out that what is the match between the bid and the sale, and accordingly, it can execute those transactions in an atomic way. So I'm not going to the details of the steps which actually gets executed on Tesseract. You can look into the Tesseract paper for details. But the broad idea is something like that. Once you are submitting the bits and the sales on top of Tesseract, then Tesseract helps to get those bits and sales to have a kind of match and get them executed in a kind of atomic way such that both the transactions get executed or none of them get executed. So the main point behind the design of Tesseract is the use of that trusted execution environment to support cross-chain asset transfer between two different cryptocurrency networks. So any query or any question up to this point? Okay. So I see this is 4 p.m. right now. So let me take a quick 5-minute break and we'll start again at 4:05 to discuss about permission blockchain interrupt. Okay, so let us resume our discussion. So the slides are visible, right? Can anyone of you please confirm?
Yes, sir. Yes, sir.
Okay, good. So let us start talking about permission blockchain interoperability. So till now we have seen the way interoperability is supported for permissionless blockchain architecture uh, in the context of in the context of cross-chain asset transfer or type of money transfer from one cryptocurrency to another cryptocurrency. So now let us see that how we can support such kind of interoperability for a permission blockchain network. Now, these permission blockchain networks, they are by default designed to be private for a closed consortium. Different business sectors, they tend to have different group of organizations, thus having separate blockchain networks. One potential example can be, say, for example, TradeLens, which is provided a kind of trade logistics network that was developed on top of blockchain. Similarly, WeTrade is a kind of trade finance network developed on top of blockchain. IBM Food Trust, it is a kind of food supply chain developed by IBM on top of their blockchain network. So that way we have different kind of blockchain-based platform, right? And just like this permissionless networks like cryptocurrencies, these models in the permission blockchain also continue to operate in a complete isolation from one another. Well, but often there is a need for interoperation between these different isolated networks to achieve the business goal. So we'll see one example, but before that, let us see that what are the challenges that we face while developing a kind of interoperation architecture for permission blockchain network. So the challenges that we face are that first, interoperation is specifically kind of verifiable data transfer between two separate blockchain networks. Well, and remember that data transfer is something different from the asset transfer. Because in case of asset transfer, what you are going to do, that you are going to transfer some cryptocurrencies from one network to another network. So you are going to transfer some Bitcoin, and in return, you are going to get back that Ethereum. Well, so that way, the unit that you are going to transfer, that is very much predefined. So this Bitcoin architecture is predefined, the Ethereum architecture is predefined. But in a kind of permission model, whenever you are transferring certain kind of data from one blockchain network to another blockchain network, these data are very much unstructured. Well, so because these are the kind of unstructured data, so that way it is quite difficult to verify that whatever data that have been received from one network, it is the correct data and it has passed through the consensus process of that network. Well, so that way this model of verifiable data transfer is much more complicated compared to the verifiable asset transfer. Well, and this data that you are going to transfer, that has to be consistent with the source network state. So in this context, we use the term multi-party trust. So this multi-party trust basically says that when one network consumes the states from another network, it would need to establish the validity of the state according to the shared consensus view of the parties in the network. So this is something difficult to achieve because every blockchain network, they are running their own consensus algorithm, and interestingly, different blockchain platforms can run different consensus algorithm. Well, now the state of one blockchain network that have been achieved to one consensus algorithm, whereas the state of the second blockchain network that have been achieved to another consensus algorithm. So here comes the challenge that whenever I'm going to transfer the state from one blockchain to another blockchain, how the parties of the second blockchain will actually be sure that the latest updated state of the previous blockchain have been transferred. So that is the particular problem that we face in case of this kind of cross-chain data transfer over a permission blockchain architecture. So here is an interesting use case. So assume that a buyer want to buy something from a seller. So they raise a purchase order. Well, so and that purchase order is raised, say, off chain. Well, so once the purchase order have been raised, so in the next step, what they do, so they request the licensing on top of the banking network, which was developed on top of WeTrade. Well, so WeTrade is basically a trade financing network. So whenever you are requesting from a licensing from a WeTrade network, the WeTrade network will so one of the banks, say for example, the buyer's bank, they propose some kind of licensing, and then the seller's bank, they approve the licensing, and that way they comes to an agreement that, well, once the transaction, the corresponding transaction of this purchase order will be made, at that time the buyer banks will automatically transfer the money to the seller's bank. Well, so that kind of automatic transfer of money that is being facilitated by this WeTrade trade financing network. Now, assume that this particular agreement has been achieved over the WeTrade network, and then the seller, once the seller get that information that, well, that agreement has been reached, that once the item will be dispatched, during that time, the buyer's bank will pay the money to the seller's bank. So what the seller does, seller uses another blockchain network, that is the kind of TradeLens network. Okay, so what TradeLens does, TradeLens is a kind of trade logistic network. So it helps in supplying the items based on the consignment that is coming from the seller. So the seller creates the consignment. Well, and once seller creates the consignment, they need to upload the bill of landing dispatch consignment. So the carrier actually submit the bills that all the item has been dispatched. Now, once the carrier is going to submit this bill, during that time, this information need to be transferred from the TradeLens network to the WeTrade network. Okay, so once this information is getting transferred, then the seller's bank can actually request for the payment. Okay, so now once you have received this information, then seller bank request for the corresponding payment. Now here you see that I need a kind of information transfer from the TradeLens network to the WeTrade network, and the TradeLens network and the WeTrade network, they are working on two different blockchain platforms. And because they are working on two different blockchain platforms, I need a way to do verifiable data transfer from the TradeLens network to the WeTrade network and vice versa. And here you see what we are going to transfer, that unlike those Bitcoin or Ethereum, which are the kind of particular assets and they have a kind of specific definitions, here we are going to transfer certain form of data. And that form of data actually represents the state of the network. So whenever you are going to transfer the data from the TradeLens network to the WeTrade network, the TradeLens network actually contains the state that, well, the carrier has successfully transmitted the good to the buyer, and it has uploaded the landing dispatch consignment. Okay, so that consignment have been uploaded and that have been verified. After that, this particular state need to be transferred to the WeTrade network. So the WeTrade network needs a way of verifiable agreement that, well, the information that it is receiving from the TradeLens network, that particular information have been passed to the consensus mechanism of the TradeLens network. So here comes the problem, that how you are going to ensure that, how you are going to do such kind of verifiable data transfer from one blockchain, one private blockchain network to another private blockchain network. Okay, so any doubt or any query regarding this problem? Okay, so and remember that as I was trying to emphasize, that this particular problem is different from the asset transfer problem that we have seen earlier. Well, so that is the reason we cannot use a protocol like HTLC here. Well, because it is not only about transferring one Bitcoin from one network to another network. Rather, here I am going to transfer certain kind of unstructured data, rather the state of a blockchain. Well, And that state of a blockchain needs a kind of verification at the other network. Whereas in case of asset transfer, while you are transferring one Bitcoin, you do not need to verify that that Bitcoin is actually a Bitcoin or not. Well, so that verification is very much inbuilt. But here we need that kind of additional verification. We need to see that the information that is being transferred from one blockchain to another blockchain that have been passed through the consensus of the previous block. So any doubt about this particular problem statement or the way this data transfer over the permission blockchain is different from the asset transfer in the permissionless blockchain? Okay, so I hope that the problem statement is clear to you, all of you. So let us see that how we can build up a solution. Well, so the solution can be built in this way, that each data or block in a network has a set of endorsement or signature for consensus. Okay, so how do we reach to a consensus in a permission model? So if you have learned about the consensus protocols in a permission network, you will see that it is based on collective endorsement. That means the parties who are going to agree on that data, they are going to digitally sign that particular data. Well, so and that digital signature, we call it as the endorsement. Now, this set of endorsement confirm the validity of a block in the network. Thus, from a source, data is accompanied with the set of signatures, which work as the attestation that this data is correct. Well, now what you have to do, you need to validate this attestation. So these attestations are validated in the destination network according to a data acceptance. Okay, so technically, this is our problem, that how we can design a collective endorsement mechanism that can be validated at a different blockchain. So here is the architecture, the way the protocol works. So this architecture contains two different blockchain network, and every blockchain network has its own consensus protocol. Now, say for example, this blockchain network is running its own consensus protocol, and the second blockchain network is also running its own consensus protocol. Now here, I have certain relay services. These relay services are running in both the network, and these relay services are actually setting up a communication channel between the two networks. Okay, so how the protocol is getting executed? So from the application side, whenever you are requesting for certain information from a different network, you send a request from the application to this relay. Then this relay of network 1 forwards that request to the relay of network 2 to some secured communication protocol. And this secured communication protocol actually ensures that the data which is getting transferred from one network to another network, that doesn't get tampered with during the transfer. Now, once the relay is getting that information, so the relay sends that information to the corresponding consensus protocol, and this consensus protocol actually generates the data through collective attestation. Okay, so that means the nodes which are there, the nodes which are running, these nodes will attach the information or will collectively sign the information that is being generated from this network. So this particular information will get attached will get signed from the individual participants in the network. Now this collectively signed information will be transferred from one network to the second network. Okay. Now, once you are receiving that information in the second network, then that received information will also again go to this consensus protocol, which will actually validate the signature. Okay. Now, to do this signature or signing the message collectively by multiple authorities and validating the signature again to multiple authorities, you can use techniques called multi-signatures. Okay. Multi-signatures. So these multi-signatures, so there are different kind of multi-signatures are available. So one particular encryption technique is called BLS encryption. So you can look into this BLS encryption technique. So that actually provides such kind of multi-signature architecture through which you can collectively sign the information in one network and transfer that data to the other network. And the participants of the other network can actually find out that, well, the things got signed by the correct parties. Okay. So here is the protocol overview that the steps are as follows. That the proof request is generated consisting of a verification policy, which has to be made by the source network. Then you check the access control policies. Then the response data along with the proofs, that means the endorsement, the collective signatures, is sent back to the relay. Then these proofs are validated against the verification policy. Okay. So that means whenever you are getting the information from network B to network A, the parties who are there in the network B, they are going to collectively sign the information. And once that information is received by the network A through the relay services, then the parties at the relay network A, they are also going to validate that collective signature by using the cryptographic multi-signature policies. So this is the kind of steps of the entire protocol. So skipping it for the interest of time. So any query about this particular architecture? Yes.
May I ask you a question? Sir, actually, this relay is about what? It's a hardware or software. It's a.
This is a software service.
This means if we visualize one blockchain network, okay, so it consists of number of computers, or you can say number of computing devices, okay, and they are connected to one network. And if you think like that, the entire inter-network is a network altogether. Okay, so if we segment one blockchain where number of blocks are connected, like they are in a particular blockchain, and other set of nodes which are also in a particular blockchain, but they are altogether connected by internet. Okay, so how you are identifying or these relays or these nodes actually?
Actually, the relay services, so typically in a blockchain, see, in any kind of blockchain network, you will have an user interface through which you are going to enter the details, you are going to initiating the transactions and also. So this relay service is nothing but a kind of entity on that user interface. So it is conceptually, it is a single entity, but implementation wise, it is a kind of distributed entity. So it is something like that. Say, for example, I am a part of one network, the blockchain application that I am running in my machine that has a relay service. Now, if I want to transfer certain information to other network, other blockchain network, I need to take help of that relay, the instance of the relay service, which is running in my machine, and send the information through.
Oh, okay, so suppose for one network, you are saying, means what I understood, that every node is having that relay service.
Right.
Okay, so when like one node from one blockchain is trying to send some asset or any kind of thing to other node in another blockchain, so actually how that the first node will know about the second node?
That you actually see that. So, for example, if I go to that earlier diagram, yeah, this example. So this is between the buyer and the seller. So you are setting up a kind of purchase order with a seller. Well, now here, say for example, whenever I am going to do a kind of cross-chain transfer, you see that the seller, it is the participant of both the network. It is participant of the WeTrade network as well as it is the participant of the TradeLens network, right? So the seller actually works like a gateway to transfer the information from the TradeLens to the WeTrade network. So the relay service which is running at the seller, it knows that this particular node is connected to both the blockchain network. So whenever you want to make a transfer of the information from the TradeLens network to the WeTrade network, what you do, that you take the relay instances for the TradeLens network which is running on the seller machine. At the same time, the instances of the relay service which is for the WeTrade network, which is running at the seller's machine, and those two relay will talk to each other to transfer the information from the TradeLens network to the WeTrade network.
Okay, sir. Thank you, sir.
Any other query? Okay. So, in the remaining 30 minutes, let me quickly go through in one of our recently accepted work, which actually talks about a concept of blockchain interoperability, and that actually developed a platform to support interoperability between a permission blockchain network and the permissionless blockchain network. So till now, what we have seen, so this HTLC or the hash time lock contract that was used to transfer asset from one open or permissionless network to another open or permissionless network. Then the kind of architecture, relay-based data transfer or the collective signing-based architecture that was used to transfer data between two different permission networks. And now we are going to see an architecture that you can use to transfer information from one permission network to another permissionless network. Okay, so it is between two different classes of blockchain networks. So the core idea of this problem is as follows, that we have different kind of online service providers which offer services to the consumers. So the consumers are the end users here. And these service providers like Amazon, eBay, Alibaba, Make My Trip, all these service providers, they use a web interface or mobile app for communicating with the consumer. And this kind of service providers can be different domain like the e-commerce service providers like Amazon, Alibaba, eBay. There can be cloud service providers like Azure, OnApp. There can be media service provider. There are logistic providers like Make My Trip. And that way there can be different such kind of service providers which are. Now, what can happen that I can put up these service providers in a common blockchain platform. So multiple service providers can come into an agreement to collaborate and provide the services to the customers. So, for example, we have different kind of hotel networks, right? So where you can search for a hotel and then you can book the hotel. Then Make My Trip is a network of different providers. Right? So you can actually use Make My Trip to book train, bus, or flight. So that way, this kind of service providers are they can come to a kind of common platform or common agreement to collaborate and provide service to the end user. And the objective is to gain access to the common larger set of end users. Well, often they offer wide range of services under the same platform and meet user demands by sharing the resources. So many of the times you can see that are very common in case of shared cloud resource or the cloud marketplace like OnApp, that when one cloud service provider is not being able to provide you the sufficient storage capacity that you are asking for, they will lend the service from another cloud service provider and provide it. Good. So the examples are like there are different sellers under eBay, Amazon, and in eBay, Amazon, this kind of things are common, that when one seller doesn't have the product with him or her, they actually buy it from another seller and then sell it to the customer. Well, similarly, hotels under Trivago. Well, so that actually comes to such kind of agreement and form a network. So such kind of network we can model with the help of a kind of closed blockchain network or a permission blockchain network, right? Because this is a kind of closed consortium. So the existing consortia are actually kind of centralized, follows a kind of centralized architecture. So for example, I have an e-commerce platform like Amazon where multiple sellers are subscribing and the consumer is using a common gateway to that e-commerce platform to reach to the seller. Similarly, in the cloud marketplace, we have this OnApp market where different small cloud service providers, they can collaborate and provide the cloud services to the end users. Now, the limitations of this kind of centralized architecture is that it is usually governed by a single authority, like a service broker or a marketplace, or that way there is a possibility of unfair business advantages to the broker. and only the service provider or the marketplace provider is responsible for communicating with the end user. Then you need to share the profit with the central broker. So for example, the seller need to share the profit with the Amazon, or the hotel owner need to share the profit with Trivago, and so on. And that way, that kind of services are not only costly, but also there are kind of security concerns in terms of single service providers. Well, so our objective in this work was to design a transparent, decentralized architecture for service providing consortium while eliminating any kind of centralized broker or market. So we did not wanted to have any kind of such kind of centralized broker or marketplace in the e-commerce platform. Well, so the architecture that we had thought of, that well, we need to move from a centralized architecture to a complete decentralized architecture, and that we can realize with the help of a blockchain. But the requirement is that we need to have a kind of unified interface through which the consortium members can communicate with each other, and the consortium members can share the information with the customers. There need to be a way to have an agreement among the service providers. Let's say, for example, for a particular product, what is going to be the common price and so on. And you need to provide a secure access to the resource and information. Say, for example, whenever you are booking a hotel or over Trivago or booking a flight on top of Make My Trip, there need to be a secure way to transfer the booking confirmation from the corresponding seller to the user who is getting the service. Well, now there can be multiple different challenges. So first of all, that the service providers can show Byzantine or the kind of malicious behaviors. The consumers and the customers can also show malicious behaviors. Well, and the third problem is that because we do not have a single trusted spokesperson, then how I can ensure the verifiability and confidentiality of the information that are being transferred from the platform to the user. So for example, one hotel in Trivago that can behave maliciously and that can transfer a malicious booking ID to a particular customer. Well, so the question comes that how you are going to prevent such kind of malicious interfacing on such kind of distributed or decentralized architecture. Well, so there are certain works that have been focused on this kind of architecture. In the interest of time, I'm just skipping those related work, and I'm directly going to the architecture that we had thought of. So our architecture actually considered these 4 different kind of attacks on the system. The first one are the kind of Byzantine faults. So we considered that the service providers as well as the consumers can be Byzantine faulty. That means they can show malicious behavior. But at most 1/3 of the service providers or that users, they can be Byzantine faulty. So that is the kind of standard guarantee for any kind of Byzantine fault tolerant consensus protocol. Then there can be a possibility of Sybil attacks. That means the end user or the consumers can create multiple accounts or identities for accessing the consortium services. There can be impersonation attacks. Say, for example, as we are going for a decentralized consortium and it doesn't have a single spokesperson, so a malicious service provider might try to deceive a consumer by posing as the consortium spokesperson. Well, and finally, there can be the leakage of sensitive information like that hotel booking confirmation or the kind of flight booking confirmation that can be revealed by the consortium because it is a kind of complete decentralized architecture. So from the architectural side, what we see that we'll have a set of service providers. The consumers are going to send the service request to the service providers, and then the responses are going back to the consumers. Well, and in between, I need to process the request. And when we are processing the request, I need to have 2 different requirements. The first one is I need to define a decentralized consortium collaboration method which will provide an interface for the agreement on pricing, catalog, policies, and so on. It will schedule the request coming from the consumers, and it will maintain the confidentiality of the service provider's information, and it will preserve such kind of confidentiality. And at the same time, I need a decentralized consortium interface which can provide an agreement on each user request. It can provide an agreement on the ordering of the user request, that in which order the user request has came. And remember that both the users and the service providers may be Byzantine faulty, so the interface should take care of that. Then the service responses which are coming from the consortium to the end user, they must be verifiable by the end devices, and the confidentiality of the response also need to be preserved. So these are the kind of our requirement in two different aspects. So as we have mentioned that we can use blockchain as a platform. So we can utilize blockchain to develop a consortium for the service providers. So we have utilized that, but the challenge here is that we have two different kind of blockchain network. One is permissionless network or the public network, and the second one is the permission or the private network. Now this private network can be suitable for service provider collaboration, because the service providers actually form a kind of closed network, whereas this permissionless network can be useful for the end users. Right? So to design this decentralized consortium interface, what we have done that we need to think of a way that how user request reach to the consortium, because we do not have a single spokesperson for the consortium. So that way we do not have a single web portal or address available for communication. So we can use simple solution like a broadcast for the consumers to the closed network. So that kind of broadcasting solution will not work, because the messages might be lost or messages might arrive out of order. And as you have mentioned, that the consumers might also be Byzantine faulty, and they can try to partition the consortium. So they can try to send one set of requests to one set of service providers and another set of requests to another set of service providers. Okay. So we need to guarantee the safety and the liveness property of the consortium. So the safety property says that no faulty service providers receive the same set of consumer requests and in the same order. And liveness property says that all non-faulty consumer requests are eventually received by the consortium. So to design this architecture, so let me not go to the details and try to explain it with the help of an architecture that how it actually works. So the core idea is that, well, these users or the consumers, they are the part of a public blockchain network, which is providing you the interface with the service providers, and the service providers are part of a closed blockchain network. So the consumers are in an open network and the service providers are in a closed blockchain network. And I need to support an interoperability with this closed network to the open network. So how it works, say the consumer, send the service request. Now this service request propagates like a transaction, like a blockchain transactions in the open network. It goes to the miners of the open network. The miners validate the transaction and put the transactions in a public blockchain. Okay. So in that public blockchain, I have a block number, which is denoted that in which block that transaction has been put, and I have an offset that basically tells me the ordering of that transaction within that. Okay. Now that way, every service request that is coming from the consumer, that is being put on a public blockchain network. Now, once that transaction is there, so all these transactions from different consumers, they form a public ledger, a public blockchain network. Now, the service providers, what they do, the service providers picks up the transactions, that means the service request from this public blockchain. Well, now once the service providers are picking these transactions from the public blockchain, what they do, they initialize a smart contract, which we call as the propagation contract, and send an endorsement. That means if that service provider agree on that transaction T1 on the public blockchain network, it sends an endorsement to the corresponding private network of the service providers, and it goes through a BFT consensus mechanism, a Byzantine fault-tolerant consensus mechanism. Now, once that consensus is reached, that means multiple service providers agrees on the common ordering of a transactions that have been picked up from a public ledger, then that information is being put on a private ledger or a private blockchain. Well, now remember that this private blockchain is maintained by the service providers, and this private blockchain doesn't have any access to towards the consumer. So the consumer cannot access, or the consumer cannot know what is going on that private ledger. It is just for the kind of collaboration purpose between all these service providers. Well, so the consumer only see the information which is available in the public blockchain. Okay, so the service providers picks up the transaction request from the public blockchain, and then it goes to a consensus, and the information is being put on the private ledger. Now, that way, every service provider is going to put up the information on the kind of public ledger, private ledger. Now, that way, what we do that once multiple service providers are endorsing the transactions and putting up in the public ledger, we actually see that whether there are sufficient number of service providers which is endorsing the transactions in the private ledger or not. If that is so, then we pick up that particular transactions for processing, because now at that stage we are sure that these transactions have been endorsed by majority of the service providers. So that means the service providers agree to execute this particular transaction. Okay. Now to transfer the response, after processing is done, to transfer the response from the private blockchain to the public blockchain, we use this method of collective signing that we call as the COSI, with the help of BLS and crypto system. Again, in the interest of time, I am not going to the details of the BLS crypto system, but in broad, it is a method where multiple parties sign a common message, and that collective signature is transferred along with the message. So the consumers or the users will verify that collective signature to see that whether the message is a correct message or it is a faulty message. Okay. So here method for transferring the response using the collective signature. So I have this private ledger that have been formed the way I have shown it to you earlier. Now we execute another smart contract that is called the scheduling contract. What that scheduling contract does, the scheduling contract actually process the request for the end users. Now, once the scheduling contract does this process of the request, it again goes to a BFT consensus, and the response is put back in the corresponding blockchain. Okay. Now, once we are putting back the response to the corresponding blockchain, then this response is getting signed by multiple service providers with the help of that COSI protocol. So this COSI protocol uses three kind of architecture for collective signing. So you can look into the COSI paper to get an understanding about how COSI works. So it actually does this collective signature, and that way the message gets propagated to all the service provider, and all the service provider signs it, and the collective signature is segregated. Okay. Now, once you get that collective signature is transferred to the public blockchain, and the miner actually verifies that signature. Okay, so miner checks whether the signature is correct or not. If the miner finds out that the signature is correct, then the miner puts up the updated signature in the public ledger. Okay, so once the information is there in the public ledger, then the consumer can pick up the information from the public ledger. It can validate the aggregated signature and decrypt it to find out the final information. Okay, so here at the same time, whenever we are doing the signature, that signature is also put up in the private ledger for the auditing purpose, so that if later on some other parties wants to see that, well, whether this signature have been passed through the collective signing mechanism, you can do that by looking into the private ledger. Okay, so that is the kind of core idea of the entire protocol, which actually says that you can see that we are using two different blockchains to create the interfacing, one private blockchain and another public blockchain. And then we are designing a method, we have designed the method, or we have designed the solution to transfer the transactions from the public ledger to the private ledger, and then process it on top of the private ledger on using smart contract. And once the processing is done in a secured way, we try to provide an architecture to send the response back to the public ledger. So that is the kind of entire idea of the protocol. So we did quite a large set of implementations of this particular protocol in different application scenarios. Like we have developed a cloud federation architecture with the help of this particular system, and we use two different permission blockchain platform like Fabric and Barrow, and that public blockchain platform that have been implemented with the help of two different Ethereum network, Ropsten and Ringbear. And we did a kind of large scale testing of the system. So this is a kind of test bed implementation that we have done. So we had three different service providers having the cloud service providers. On top of that, we created a network using this Docker Swarm overlay network, and then different kind of blockchain services that have been implemented on top of this service providers implementation. And the clients, they also have a kind of user interface that have been designed. And finally, this entire system have been put up and then get executed for several months, from where we have collected the statistics data and finally tried to understand that how such a system performs in reality. And what we actually see that the kind of parameters like the latency at different stages, they are quite low, and we can actually come to a consensus and can do that verifiable data transfer quite quickly, well, compared to different environment which are available. So I'm not going to all these details about the different performance metrics that we have measured. That Infocom paper is already available in public, so you can actually look into that paper to get the details. Also, this implementation has already been open source. The implementation is publicly available, so you can download that implementation and try it yourself by setting up a network and then transferring data from a public blockchain to the private blockchain and vice versa, and to see that how it works in reality. So that's all from my side for today's talk. So let me see if you have any query or any question. So any further query from the participants?
Participants, please, if you have any question, ask. This is a good chance to learn.
Yeah, you can put it up in the chat box as well. Okay, if not, then let me just conclude by giving you an idea about what different things that we are doing at our lab. Okay. Yeah, so I typically run this research laboratory called System, Mobile and Network Research Lab at the Department of Computer Science and Engineering and IIT Kharagpur. So currently we have 11 members in the lab, not 11, so this slide was actually around 6 months old. So currently we have around 14 members in the group, and 4 have already graduated. In the lab, we have various industry-supported projects from HP, Intel, IBM, Bell, Samsung, TCS. Well, and from the group, we have consistent publications in top venues, including Infocom, Parcom, TAP, ICNP, Spatial, in all these top conferences, which you will see that I think rarely you will see any paper from India in those conferences. And what I can say that currently in the system research, this particular lab is doing at par with many of the top research labs across the globe. And even the students are being supported through different kind of industry fellowship, like the TCS Research Fellowship. The TCS Research Fellowship is given by the TCS to different institutes in India. But I can proudly mention that in our lab, there are students who got this IBM Global Research Fellowship. So this IBM Global Research Fellowship is given to around 10 to 12 students every year, and they have been selected across the globe. That means across different countries. So we have almost one fellow almost every year. We got it for the last 4 or 5 years. And that is possibly the only institute in India from where you will see IBM Global Research Fellowship student who got IBM Global Research Fellowship for doing research. So in the lab, we are working on different aspects of computer systems and mobile sensing and HCI. In the system side or in the network side, we are working on network virtualization, network applications, the adaptive video streaming, storage network, container network, network traffic analysis, the different kind of system aspects of blockchain. Indeed, with blockchain, we have a very strong collaboration with IBM Research. Even the students who are working on blockchain here, they have been directly contributing to the fabric development, Hyperledger fabric development. So we are strongly collaborating with IBM in this aspect, IBM Research in this aspect. And in the mobile sensing and HCI front, we are working on developing different kind of smart transportation application, human sensing and human activity monitoring, doing work on data analysis from the smart home, so building up different kind of innovative sensing systems and HCI-based platforms. So these are the kind of a broad spectra where the group is currently working on. And the reason that I am just doing this kind of shameless publicity about the group is that currently we have multiple funded projects where we have open positions. So if you know any good student who is very much motivated into academics or very much motivated in doing higher studies or research, you can always point them to my research group, and they can directly write back to me. So I'll be happy to have a discussion and to see that whether they are suitable for the group. So that's all from my side. Thank you all for attending this talk and giving me this opportunity to share some of our works with you in today's lecture. Yeah.
So thank you, sir, for your nice talk. But before that, being the coordinator of this course, I must say that I follow you in Facebook and other places also. Okay. So I really appreciate your presence here. You have given very nice talk, and it's a new technology, so there are very less number of experts in this field. So we got this opportunity to have you with us, and we learned many things. And personally, I want to continue keep in touch with you so that we can learn something and do something together.
Sure. So I'll be happy to visit NIT Silchar sometime because as I spent a long time at IIT Guwahati for nearly 10 years there, and means I have many of my friends there in Silchar as well. So because of this pandemic, all our travel got restricted. So that's a kind of unfortunate thing. But I hope that this pandemic ends very soon, and we'll be able to physically meet and have a kind of nice interactions over there.
Yes,
so thank you for
inviting you visited long back here also.
Yeah, right. Yeah. So yeah, thanks again for inviting me in this.
Okay. Thank you, sir.
And thanks to all the attendees for giving your time.
Okay, sir. Bye.
Okay. Thank you, everyone. Take care. Bye-bye.
So, dear participants, today this is the last session. So, next day, there is the 5th day of this FDP. There we'll have 2 lectures, and then the last session will be on validity ceremony. And in the validity ceremony, I have already shared with you that you have test, and then after that we have some speeches, from the experts and all. So thank you for today. We will come back tomorrow 9:30. Thank you.